So in this lecture, we'll see this Python program for implementing the crossover and mutation operators. We'll write the program and run it. So if you see, this is the same program in Python which we wrote, and it is showing the objective function. So now we'll just see what things we have added new. So this was objective function, then fitness function, pop string, population string, so on, and decode individual chromosome to individual population, how to generate, interchange the populations, then creating the mating pool, and then crossover in mating pool. Okay, so this is for this part we were doing. This was selection operator. So selecting the fittest individuals, and now we'll see in the mating pool what this crossover actually does. We have already seen in the theory class that how the crossover operator is done. So if you see, this is the definition of the function crossover in mating pool. It takes mating pool itself as an input, population size, string lengths, and crossover probability. So we have seen that what they mean. Okay, so these are the things it will take, and then it in a loop it will run this one, and it finds a random number rand, and once that rand is greater than or less than the crossover probability, then the first thing is uh, it it takes the crossover point. Once it is clear that okay, you have to do the crossover less than crossover probability, then it chooses the crossover point CP, and this is a way to uh, generate a random number, integer random number between a uh, given set of values, that is from 0 to string length could be from 0 to this total string length of the chromosome. Okay, so so it's -1 because if you know in this the numbering starts from 0. So I'll just cut the original segment first, okay, because after changing that may be problem. So original segment is first taken, that is that crossover point where it is from the it is the first one is saved. Okay, then in the mating pool what we do is that particular crossover point is exchanged with the next one. Okay, so whatever is there in the next one, because this is already saved here, because this has to be put on the next parent. Okay, so this is there, it takes the that value, whatever cross point value it is, 1 or 0, to the ith value, ith individual, and then this I plus 1th individual takes this original segment. Okay, so it is like swapping. Okay, so this is how crossover runs, and mutation is again same process, but not exactly in the same way. Okay, here also it takes the same set of input. It takes mating pool, pop size, string length, and mutation probability. And here what it does, it runs this one and find if random number is less than r, that is the mutation probability you have taken. Okay, if r is less than the mutation probability, then it randomly uh, initiates a mutation point. Okay, so this is not crossover point, rather it is a mutation point. And then here it is randomly changing that mutation point. So if it is already 0, it may be 0 or 1. So a mutation may, it actually further reduces the probability of mutation, because if it is already 0, the random value may be again 0, so no change. But here I have taken it as, and you can take otherwise also. If it is 1, then make it 0. If it's 0, then make it 1. So both ways it will work. Now let us see test this two new functions which we have written. Okay, the crossover and the mutation. So for running this, if you remember, all the things are there. String lengths are there, upper bound, lower bound, I have taken a population size of 50. I am setting crossover probability as 1. This is set because I want that to test the program, I want the crossover must happen. Otherwise, I won't be able to see the crossover if the probability is less and crossover may not be there. Okay, similarly, I'm also taking mutation probability on, but in actual program, it will not be 1. It is just for testing this two functions I'm putting so that the crossover happens and I can see the results. Okay, so this is the same program. Okay, it is finding the individual chromosome to individual population, then finding the fitness and objective function, and from that objective function we are uh, taking the selection probability, then cumulative probability, and from that cumulative probability we are doing the selection and creating the mating pool. So up to this point we have already seen. What I am doing is, after creating the mating pool, I am choosing certain individuals so that I can clearly see that if the what was the result in the mating pool after selection, then the mating pool is then crossover and mating pool function is called, and then mating pool changes after that, and then I can see what happened, the crossover has happened or not. And if the mating pool is after mutation, I'll again see the mating pool. The same set of individuals are being seen here, 4, 5, 6, and 7. Okay, these individuals are seen. So we'll run the program and see this is actually working correctly or not. Let us run over here. Okay, so if you see, this is the two individuals and these two individuals are different, so there is a chance that there will be some crossover. So I can see 4, 5 after selection, then I can see the same individual 4 and 5 after crossover. So 4 and 5. So if you see 1, 1, 0, 0, 1, 1, 0, 0, so no here, 0, 1, 0, 1, no crossover. No crossover, and here no crossover. So if you see here also no crossover, here also no crossover has taken place. Here also no crossover has taken place. 1, 0, 0, and 0, 1. So no crossover has taken place. It may have taken place on the same set of values. So let's say 1, 1. Second one is also different. So there is a chance here. 1, 0, 0, 1, 1, 0. Here 0, 1, 0, 1, 1, 0, 0, 1. Same. No crossover has taken place. No crossover has taken place here. Here if you see this one 1, 0, and here it is 0, 1. So in this individual there, this crossover is clearly visible. Okay, rest only one crossover takes place, so this is clear. In uppercase it may be between 1 and 1, so there you won't be able to see the change. Similarly, you can see the mutation also. If this was the crossover, you can just check the mutation has happened or not. It is also random, so even mutation may happen and it may not be visible. So this after mutation, if you see this individual, which I'm showing to cursor, it remains same. So no problem. It may have same values, and then it is here, here, here. So because it is randomly changed, so it may have changed to one, has may have changed to one itself. So you may not get any see any change after mutation. So here, if you see 0, 0, 1, 0, 1, 1, 1, 0, 0, 1, 0, 0, 1, 0, 0. So here also you're not seeing the effect of mutation. 1, 0, 1, 1, 1, 1, 0, and here you don't see effect of mutation at present, but crossover you could see. So I can run this program once more. Possible in that case we will be able to see the effect of mutation. So I can compare this one with this one. Okay, so if you see here 1, 0, 0, and so not in the first one, in the second one you see 0 1 0 0 0 1 remains same, 0 0 remains same. So in the second one also you don't see any change. 0, so 0 0 1. Here if you see this one, it is 1 here and it is 0 here for the same individual. So mutation has taken place here, and obviously no other place it will take because only one bit is changed. And you can also check if there is, here also there is a mutation, so 1 has changed to 0. So that is how this is working. So this is for mutation part and the crossover part. Now once this is over, now we can close the loop. Okay, what do we mean by closing the loop? That means now a new mating pool has been formed, and that mating pool is now the new population. Okay, so that is what it has been done here. New mating pool is again made as population, and now you can repeat this while loop. Okay, so now we'll see that how this loop is closed. Okay, I'll just go to that part and see how that loop is closed. Closing the loop. Okay, because in Python you have to maintain that tabs, because of that only. So you have to write the program. If you want to have an extra while loop, then you'll have to see how to do it. Okay, you have to put the tabs and spaces properly. So here what I am doing here is you have taken all this crossover probability, mutation probability, population size, and so on. Okay, and if you see I have taken this is, so just we'll just sum up what we have done. So this is the objective function program. Okay, so you can make active whichever you want. You can write several objective function and make one of them active. This is fitness value program, then population string program, that is generating the population, then decoding the population values as a string values into a individual values, then finding that decoding the string into a individual, and here you do the with the whole population you find the individual values from the chromosome, and this is creation of mating pool through selection, and the last one is crossover, and then you have mutation. Okay, now let's see how we are running. We are deciding the number of variables, each variables, the string length and upper bound and lower bound. I'll just upper bound and lower bound is 0 to 5, and this population size I've taken as 100. This is crossover probability and mutation probability, and these are all the things which have been initiated earlier also we have seen, and this is the starting initial generation of population, and from here we are closing the loop. Okay, because the pop, so I am taking, let's take smaller number of this one, so that say 100 generation, maximum generation, and then generation count, and there is a while loop. In this while loop what we are doing is we are finding the individual values from the chromosome which were generated in the as a population here. So population is first generation generated as a chromosome, and that chromosome is taken as made into individual population. Then here we are calculating the objective values and fitness values of each of them. Then I am taking the best value. So this is a option from this objective values. We'll see what are the best values available, so that when we stop the program that we get. Okay, so that is minimum of the objective function. Okay, this is the individual objective values, and this is the way to calculate the minimum and get the index also. So this is to get the index, so that I can, from that minimum value I can find what is the value of the variables. Okay, so best, so once I get where that maximum minimum lies, I can find the best value index, I can find the best individual. Now, so from there, now what I'm doing is finding the fitness cumulative sum. So here, if you see, the cumulative sum is always put to 0 again and again, and individual probabilities are calculated here. So this is selection process. After this selection process, you create a mating pool. Okay, then mating pool, you go through crossover, then mutation, then put the mating pool as population, and now generation count is incremented. So here the while loop ends. Okay, so if I want, I can write the comment end of while loop. And now from here, because it's very it's not easy to get where it ends, because it is taken by this length, that is how much tabs you give. Okay, so again, now then the individual population, same the things which we saved earlier, we just see what is the best population, best value. Individual population is just to show what are the values, final individuals or final population, best values, and best individual. Okay, so I'll just run this program, and this now loop is closed, for it will run for 100 runs and then it will stop. So best value comes out to be this one, and this is actually the program which best value. So if you see what was the objective function for this, if you see this program for which objective function it is running, we selected two objective functions. So for one of them it is running. Okay, so this objective function it is running for. Okay, so in this objective function I have also written what was the answer. So it is 1 and 0 was the answer, and the value was around 2.667. So it is quite close by that way. If you increase the number of generations, you can get better value, but that is the one way to do it. I have taken the simplest way to close the loop, that is counting the number of generations. This has run for 100 loops. The best value is this, best individual is this, and this is the population which is there. So if you see the population, it is quite close to 1. Most of them are very close to 1. So all the population is trying to come to that value. Okay, so this ends the, in fact, the very simple GA program. You can write more complicated for finding that for how many iterations it has to run, what is the minimum, for how many iteration the objective value remains same, and so on. So other variations are possible in stopping criteria, as well as you can do other variation in crossover and so on. Okay, so that is all. We stop here for this one. Thank you.